All right, great. So welcome back, everybody. Um, and we're going to get started here. I'm going to get, all right. Okay, great. All right. So thank you all for coming back after the break. I hope you're all here. If you could, again, for those of you here, if you're unless you're suffering from bad quality of transmission, I'd really appreciate if you can turn your video camera on. All right. Okay. Hey, before we get started, so once again, remember there's a little raise hand button. So take a second to find that button. Don't press it yet. I have a question for you, but make sure you identify where that raise hand button is. If you don't know where it is, I don't know how to help you because you can't raise your hand to tell me. All right. Here's my question to you. In the past 1.5 hours of our lecture, how many of you had really did not? How many of you had bad video or audio quality with Zoom? Could you just raise your hand? If you are on, maybe you're not even on Zoom if you didn't have bad quality, but you just raise your hand if using Zoom you had bad video or audio quality. Okay, nobody's raising their hand. Maybe all the people who had bad quality are not on Zoom, maybe they're just on YouTube, but there's a lot of you on Zoom, so let's see. Let's see some new messages here. Okay, so maybe one person at least did. Okay, all right. For those of you who are here on Zoom right now, Um, can you raise your hand if you feel that the Zoom video or audio quality is better for you than Google Meet? Okay, so quite a lot of you are raising hands. All right. Okay, so there's obviously a big difference here. Okay, stop raising your hands because that's everybody. Not everybody. There's a lot of people. Okay, so there's clearly a big difference between Zoom and Google Meet for big classes. Again, I noticed that for small classes it's not a concern, but for big classes it's apparently a big concern. Okay, great, good to know. My TAs and I were like, our weekend was racking our brains about what to do about this. So I think we have at least a solution that we can use for 2 more weeks. All right. Okay, thank you all very much. And again, sorry it's taken us a couple of weeks to kind of figure out how to get this going, but it should be smoother from here on. All right. Um, all right, let's move on. Um, so I want to talk about a new data set, a new problem space, and a new way of thinking about data. All right. And I think many of you are familiar with this form. So let's take a look at it, maybe from new eyes, maybe from old eyes. We'll see what's going on. Okay. So you're back from the break, new data set. We're going to look at this data set here, which is about athletic performance. All right. And let me explain what the data set is. Um, the data set, if I can, let me try to load it in, let me just try to load it in R and let me then view and take a look at it. So this is my data set. I think you can all see it. And in it, you can see that there are about 10 columns and about 33 rows. Let me explain what each of these are. This data set is from a sporting event called the decathlon. Raise your hand if you know what a decathlon is, or you've heard of the term decathlon before. Decathlon. Anybody? Nobody? Nobody has heard the term decathlon? I'm shocked. All right. Well, all right, one person says yes. So decathlon is essentially a sporting event where every athlete who's competing in it has to actually compete in 10 different sports. All right. So it's a sporting event where every athlete has to do 10 separate sports. And then we get an idea of how good you are as an all-round athlete. So not just how good you are at running or not just how strong you are, but everything kind of combined. Obviously, not everything, but many things. Um, oh, someone just pointed out that NTHU and NYCU have a decathlon competition. I'm a little shocked. Okay, all right. Um, so the DEC in decathlon um, means 10. So that's like the same word in decimal. Decimal is the counting system from 0 to 9, and then 10 is a special number with 1 and a 0, and that's a decimal system, all right? Um, just, but because English is such a weird and unorganized language, there are places where we use DEC where it's not 10, like December is the 12th month, but it's called December. Um, Probably because it used to be the 10th month, but then a couple more months got squeezed in the between, and then it's now the 12th month, unfortunately. Decile is like percentile, but for the top 10% is often is a decile. All right. So DEC means 10 often. The athlon, athl tells you about athletes. It's about athletics. It's about physical performance. All right. So decathlon is a sporting event where athletes take part in 10 sporting events, in all 10. As you can imagine, it's extremely rigorous, and many people would simply not be able to do this. So you have to be a really good all-around athlete. So it's a really interesting um, competition to study and a really interesting data set as well, right? So here's what we're going to try to do. Um, we want to ultimately, I have a few questions about this data set. One is, how do we pick a winner? There's 10 sports. Who is the winner? I mean, nobody's going to win all 10 sports. Somebody's going to be good at some sports, somebody's going to be good at other sports. How do you decide who wins this game? Like, who's ranked number one, number two, number three? Like, that's the question. Okay. Um, and the second question is, this is supposed to be measuring athletic ability. Well, what is athletic ability? Like, what is that? I haven't even defined that yet. In fact, I don't think we can define that. Um, it's athletic ability is being good physically at, I don't know, in many ways, but which ways and how and what is it? So this is our data set. This is our concept that we're trying to measure. And I'm going to use the word construct because we're going to try to statistically measure this concept of athletic ability. So it's a concept we're interested in understanding through data is what I'm going to call a construct. Okay. And I've talked about constructs before in class when we talked about measurement error and other things. We said our data is so far away from our constructs or our concepts. Well, here's our concept or our construct. It's athletic ability. All right. So athletic ability is what we're interested in. I don't even know how to define it yet. But what I do have is I have this interesting data set that might be able to help give us a glimpse into athletic ability, because here there are 33 athletes, so row 1 to row 33, and each of these athletes has participated in all 10 of these sports. All right, in all 10 of these sports. So this might be an interesting data set to understand what is athletic ability. Like, what are the aspects? Like, if I had to say two or three things about athletic ability, what would they be? I don't know, but maybe the data can help me answer this question. Okay, and and I know there's 10 sports, but why are there these 10 sports? Does anybody want to guess why these 10 sports were picked? Anybody? Go ahead, type your answer. While you're typing your answer, I'm going to ask, what are these 10 sports? Okay. First of all, this is 100 meters. I've tried to show an icon of somebody running. Oops, excuse me. So that's 100 meters. It's a 100-meter sprint. So you run as fast as you can for 100 meters. Okay. There's another event called long jump. I think the picture helps you understand. You run a long way and then you jump a long way, hopefully. All right. Then there's the shot put. And do you all know what a shot put is? It may be not a word that translates easily. I'm sure there's a Chinese word for it, but I don't know what it is. Yes, one person does. Gil, thank you for the link to the decathlon on Wikipedia. Let's take a look at what shot put looks like. So I've got a little video here of a shot put. Not me, obviously, doing the shot put. I wouldn't throw it very far. But this is a lady doing the shot put. So I'm sure you've all seen this sport on TV. And bang, that's amazing. All right, so that's the shot puts. All right, so that's the shot puts, and I think you all know what it is. You got to throw that ball. So then there's the high jump. You all know what that is. You've got to run and you got to jump over a bar. Okay. Um, then there is 400 meters, and that's you've got to run for 400 meters. So this is a little bit tricky. You want to run as fast as you can, but you've got to conserve a little bit of your energy so you can cover the full 400 meters. So you can't run just as fast as 100 meters. You've got to conserve a little bit of energy. So All right, so that's interesting. 110-meter hurdles, you all know that what that is. You have to run for 110 meters and jump over these little blocks called hurdles. All right. Discus throw. The picture may not help too much if you don't know the translation. So let me just jump to video for discus throw as well. All right. Let me see if I can go to the discus throw, and let's take a look at someone throwing the discus in slow motion. So this is the discus throw. You're holding this discus in your hands, and you rotate around and you throw it as far as you can. It's a flat object that you've got to throw. All right. That's the discus throw. Great. Pole vault, I think you all know what that is. The picture should really help. You carry that stick and you plunge it into the ground and you spring off of it, okay? Javelin throw, I think you all know what that is. Even by the picture, you've got a short spear, a light spear, and you've got to throw that as far as you can. 1,500 meters, you've got to run 1,500 meters. So you've got to, it's getting closer to long distance running, but it's not really that long a distance, all right? So interesting collection of sports. Why were these sports picked? So some of you saying it's fun to watch. These are sports that participate in the Olympics. Certainly, these are Olympic sports. But this raises the question: why are they even Olympic sports? What's about these sports that's special? So before we start talking about athletic ability, we have to always remember that data is biased. Data is not like some neutral thing that comes into our lives. Data has a lot of human bias and history built into it, and we have to be very clear when we're asking questions that we recognize these biases in our data. These 10 sports are probably most closely linked to ancient Greek sports that were originally or close to some of the original sports, or maybe a little bit later that joined the Olympics. So first of all, these are Western sports. If the Olympics began in Asia, I don't think these would be the 10 sports in the decathlon. It would be probably quite different, right? There might be some martial arts or something else. There might be yoga in it, who knows? But it wouldn't be these 10 sports, all right? So first of all, before we get too far into athletic ability, do understand this is a Western impression of athletic ability, particularly from their Greek cultural heritage, all right? So whatever question we end up answering is going to be about that heritage. So let's be, first of all, very clear that that's what this data is. Okay, so when we're talking about athletic ability, we're talking about a very narrow perspective of athletic ability that comes from this Greco-Roman, Greek-Roman perspective of performance. All right, so good. So that's the bias in the data. All right. Metab, you said that the games have a similar measurement output. Could I ask you to say a little bit more about what is the similar measurement output? Because that's a very interesting point you've made that I might come back to later. Okay, but please give me a little bit more on that, and we'll as I'm moving on. All right. So these are the 10 sports, and these are the 33 athletes who competed in these 10 sports. Now, if I asked you, I'm going to ask somebody to raise their hand and answer this question. If I was to ask you, what dimensions of athletic ability are these measuring? I mean, they're not all measuring the same thing, they're measuring slightly different things. What big things are they trying to measure? Does anybody want to give me an answer? I guess you could type it as well. You can tap it as well, but any dimension. Oh, thank you, Metab. Yeah, so Metab saying all of these are measured in terms of length, in terms of distance or speed. Oh, so length or height or speed. So distance or speed. So yeah, that's a good point to make. Okay, we'll come back to the units a little later. So Halim says these measure things like power or strength, agility, and endurance. Interesting. So Halim has some expert knowledge about sports, apparently, because he's using more sophisticated words than I would use. So he's saying power or strength. So that's how strong you are. Halim, can I ask you to unmute yourself so I can ask you some questions for a moment? Okay, so power or strength, where? Like how strong their fingers are, how strong their hands are, how strong their legs are, how strong their whole body is. What kind of strength or power are they measuring? How How strong you are where? Which part of your body? Okay, so something like shot put will measure to a great degree your leg strength. And if you looked at the shot put, the lady doing the shot put, her legs are like bigger than me, like bigger than my whole body. And but you notice at the end, she had to still, after spinning, she had to use her arm to throw it, right? So is it a lower body sport or an up? What's that? You think it's more upper body or more lower body? Which one? More upper. Okay, fine. Okay, fine, fine. So at least some of the sports are measuring upper body strength. Is there any sports measuring lower body strength? Maybe high jump because you've got to literally jump off your legs. Okay, all right. So it's not just strength and power; it's two types of power, possibly, possibly. Okay, okay. You can mute yourself again. So, okay, thank you. And other things like agility, which is like how quickly you can. Well, agility is more like how quickly you can like stop and move. You know, like it's like how quickly you can turn. But none of these really seem to be measuring. Are they measuring agility? Maybe endurance, which is how long you can sustain a physical activity. So maybe something like 1500 meters is measuring endurance. But is anything else here measuring endurance? Just one sport for endurance? All of endurance captured by one sport? Anybody? All right. So it's measuring different aspects, okay? And there's a couple of ways of answering this question. One is we could actually ask, so we could also look at the correlation table, by the way, and look at some interesting correlations between these things. For example, and I haven't looked at this table in a long time, there's a fairly strong correlation between 400 meters and 100 meters. What a surprise. There's a negative correlation between 100 meters and long jump. I would not have guessed. Oh, wait. Why is that? Why is that? Does that mean the better you are at 100 meters, the worse you are at long jump, or does it mean something slightly different? Anybody? Here's a little tricky because 100 meters is measured in time, and the better you are, the shorter the time. Long jump is measured in distance. The better you are, the longer the distance. So actually, 100 meters is correlated with long jump, and if you're better at one, you're actually better at the other. The correlation is negative because one is measured in shortness of length, the other shortness of time, the other is measured in greatness of length. So there's a negative correlation, but actually if you're better at one, you're better at the other. Okay. What else is going on here? Any others big, very, very large correlations? So we had a 0.6, we had another 0.59 here between 400 meter and 100 meter and 1500 meter. Okay, interesting. There's a reasonable correlation. Oh, ooh, there's a big correlation between shot put and discus throw, the two sports we saw the video on. Okay, so those are so shot put and the discus throw. They seem to be heavily correlated. They have maybe some similarities in technique. Okay, so this is interesting. So the data kind of makes sense, and notice also there's some very small correlations which are also curious, like javelin and 100 meters. Javelin is where you have to throw that spear, like the stick. You have to throw that. It doesn't seem to be very correlated with how fast you can run. That's kind of curious because before you throw the javelin, you've got to run. You've got to run and throw the javelin. You use your body's momentum. But it doesn't seem to be about how fast you can run, but more about how well you can transfer your momentum from your body to the spear. So maybe technique is more important than speed of running. So that's kind of interesting, right? The correlation table is already so interesting to me. Anything else? 400 meters and high jump, not really very correlated. Javelin and 110-meter hurdles, not very correlated. Pole vault and 1500 meters seems to be not very correlated. All right. So now there's two ways in which we can ask what is athletic ability, what dimensions, what aspects are there what parts are there to athletic ability. One is we could either use our understanding of athletics or we could use the correlation table, and we can just use our human understanding to try to understand what is athletic ability. All right. So some people said power, some people said endurance, but these seems to be the two things that have been mentioned so far. If there's another one anybody would like to mention, go ahead. All right. Um, but these are all expert-driven attempts to extract some features or some unique dimensions from this data. All right. But what we're going to try to do today is to put aside for a moment the human driven, the expert driven approach and go for algorithms that can give us a data driven approach. So can we use algorithms which can inspect the data, and the algorithm and the data together can tell us what they think is the important dimensions of these 10 sports, okay? Because as you can see, these 10 sports, some of them are quite similar. In fact, many of these sports are quite similar to another one. We saw that shot put and discus are quite similar. 100 meters and 400 meters are going to be quite similar, um, and etc., so on and so forth. Okay, so there's a question here. There's a point here that maybe we can use a heat map. We could use a heat map, and it would be this correlation table in color form. Okay, but a heat map could give us similar information to this correlation table, but maybe in a slightly more visual form, so we can pick up things a little bit easier. All right. Fantastic. And in fact, when we look at homework problems like this on your homework or anywhere else, I would love to see some heat maps if you know how to produce one. All right. All right. Let's try to answer these questions though in a more data-driven way. Okay. Before we do that, let's try to see what it is. What is the problem we're trying to basically solve? Okay. We'll slowly work our way into the math, but I won't go into too much math today. Maybe we'll look more into it next week, okay? So let's try to understand the dimensionality of this, but 10 variables is a lot. So before we jump into 10 variables, let's do a simple problem. Let's look at just two variables, okay? Let's make this really simple on ourselves, all right? So we have, let's take two of them, 110-meter hurdles. That's the sport where you have to jump over those hurdles, but for 110 meters. And then the shot put. And I'm picking these two because to me, these two seem to be quite different from each other. Okay, so I'm going to pick these two sports to begin with and ask, how do these relate to athletic ability? Like, what would athletic ability be if I just had two sports? We'll come back to the 10 sports in a little bit later. All right. So essentially, what we're trying to do is we have a concept called athletic ability. We cannot measure it because we don't even know how to define it. All right. So much less measure it. What we can measure are these measurement items, 110-meter hurdles and shot put. Okay. What we're going to try to create is some kind of composite. A composite is some kind of variable that captures the measurement items and puts them into a single variable. All right, because if I have to compare every athlete on two sports, it's going to get a little confusing because some people are going to be really good at 110 meters, some people are going to be really good at shot put, and it's going to be a very subjective question about which one is more important or less important. Okay, so what I want to try to do is we may have to make a subjective judgment on how to weight these, but somehow I want to combine them into a single score. And that way, at least with two sports, if I can combine them into a single number, then I can start saying with these two sports, who is the best, who's the second best, who's the third best, all the way to who is the worst or least best, because they're all amazing, I'm sure. Okay. How would we do it? Well, as a human being, there's a couple of obvious solutions. One is I can simply add these numbers together with some kind of weighting associated with it. For example, I could just take your 110-meter hurdle score and your shot put score, and I could just add them together. All right. Um, and that can be a measure of athletic ability. The problem with that is I'm assuming that both sports are equally important. I'm assuming that let's say the decathlon was just a biathlon, it was just two sports. There is a triathlon, right? But there's no biathlon as far as I know. But let's say it was a biathlon, just 110-meter hurdles and shot put. I would be assuming that they are equally important So you should have trained equally in both. That's an assumption on my part. Okay. Another way of representing that is if I just multiply each one by the same constant, like half. Say half this, half that. It will give me this different numbers, but the same effective weighting as multiplying each one by one. All right. Now, somebody else, maybe a shot putter, might argue that, yeah, 110 meters is important, but I think shot put is a better measurement of overall athletic ability because you need this and that and that and this and I don't know what else. So it's possible that it's possible that somebody could say that we should put more weighting to shot put than to 110-meter hurdles. Okay. On the other hand, somebody may say, hey, that's not fair. I think 110 meters is more important than shot put. We should weight it more. Okay. How many, if you had this problem, like you are on the committee that has to decide how to put these scores together, how many of you would say weight them equally? Could you raise your hand? Not physically, you use the raise hand button. Could you raise your hand to tell me how many of you would say weight them equally? Okay, some very fair people here who are saying, I'm not going to discriminate. Oh, lots of people. Great, fantastic. All right. Wow. So like a dozen of you, or almost a dozen of you. Okay. All right. I'm going to lower all your hands now. Okay. And let me ask, how many of you would say you would favor one sport over the other? It doesn't matter which one, but you would prefer a weighting where one sport has a slightly more weighting than the other, whichever direction, hurdles more or shot put more. How many of you would prefer a weighting where one is weighted a little bit more than the other? All right. The votes are coming in. We've got about half a dozen people so far. Will the number go up? Will we beat the average waiting crowd? Anybody else? Anybody? Oh, we're at a dozen people. Great. Um, Let me pick on one person. I'm so sorry to pick on you. If your audio works, Emmy, haha, I see you. Emmy, if you could turn your microphone on and tell us why you would weight it. Everyone else can turn I'll lower your hands. Go ahead, Emmy. Which one would you weight more? Because? Oh, okay. So there's more motion involved, right? Okay, all right. But somebody can argue that's not fair. Shot put requires a lot of strength, and hurdles is not so much strength oriented. Fantastic. No problem. Different experts will have different opinions. So, all right, thank you. You can go ahead and mute the microphone again. All right. Okay, so there are good explanations for both. Some of you may feel it would be unfair to favor one. Some of you may feel no, we should favor one over the other. Maybe there's a little bit more going on. Okay. But I hope we understand that we cannot measure athletic ability. The best we can do right now is to come up with a composite score. All right. And hopefully that composite score is some representation of athletic ability. Um, okay. All right. But how would we weight it? That's the question. So I'm going to go back to a question I asked a long time ago. And sorry if it's such a big segue. Remember, so by the way, once again we have hurdles and shot put. We have a two variable problem, so we can make a two-dimensional scatter plot. This is not the scatter plot of hurdles and shot put. It's not. I'll show that to you later. But essentially, we're going to do something which will again involve drawing a line through data. Okay, and I'll tell you why we're drawing a line through data. In this case, it's going to be for a different reason than regression. But remember when we did regression, I said that a regression line is the line that minimizes the vertical distance between all these points, right? And at that time, I asked you, is this the best fitting line? And one thing we discussed in class is this is only the best fitting line from the y perspective, from the perspective of one of these variables, which is the y direction. Okay? But it's not the best fitting line in both directions. In fact, if you wanted to do the best fitting line in both directions, we would have to do it this way. We would have to find the line that minimizes the direction in that minimizes both directions simultaneously. All right. And interestingly, that's the tool we're going to use today. We're going to use a technique that defines lines and vectors that cuts through data, like the way a regression line did, except these lines are going to be finding the best fitting line in all directions. So if you have X and Y, it's going to try to minimize the direction in X's and Y's. So that means it's going to try to minimize the orthogonal direction from each point to the line. Orthogonal meaning the 90-degree direction, all right? So if this is a point over here, then we're going to try to minimize the direction straight on to the line at 90 degrees to the line. That's the direction we're going to try to minimize, okay? And this technique we're going to describe today, and I think a lot of you are familiar with it, is called principal components. And a little show of hands, how many of you, I'm not going to ask a follow-up question, so don't be shy. Can you raise your hand virtually if you've ever studied principal components before? Go ahead. I'm going to guess a lot of you have. All right. Wow. Okay. So we have keep it raised. Oh, okay. Oh, they're going down now. Boo. All right. So only 9 of you, 10 of you maybe. Okay. Okay, 9 or 10 of you. The others you may have seen it elsewhere, but okay. Let's take a look at it. Okay. So I'm going to lower all the hands and let's get going on this. So this is so we're going to use this technique called principal components. So let's try to understand what this principal components technique is, and then we'll come back to see how we're trying to use it to the data set that we have. All right. So principal components is essentially a technique that says, let's say our data looks like this. Let's say our data is in this little kind of data cloud right here. Okay. And we've measured it using X and Y. All right, using X and Y. That's the way we've measured this data. And it's kind of just, the scatter plot would look like this. All right. Now, what principal component says is the way you've measured the data, let's say 110 meters, and that's time, and shot put is distance. That's just a convenient way because you can measure those things, right? So that's why you measured it. But when we look at the data has a shape that is sometimes not exactly matching the two directions. So for example, you'll see that this data has kind of, can I draw it? Let me see if I can draw it. It'll be a little tricky. But this data has something of an egg shape. Does that look like an egg? Kind of? It's got something of an egg shape. Like it's longer in one direction than the other, right? I think you can all see that. So the data has a little bit of an egg shape, but the shape of that egg, which direction is the egg stretching in? It's stretching in this direction here, right? This red line that's running through its length here. It kind of seems to be stretching in that direction, and it's wide in this direction. Okay, so we can draw 2 lines here to show the first line, this red line, tells you the direction in which it is stretching the longest. All right, that's this first red line here. That's the axis along which it's stretching the most. And then the other red line, which is 90 degrees to the first line, is telling you the other direction in which it is stretching. Okay, So in 2 dimensions, we can define this as a shape which is stretching in, well, 2 directions because it's a 2-dimensional data shape. And it's stretching in these 2 directions. But note that these 2 directions don't really look like the directions of X and Y, all right? So the data has its own shape and it doesn't quite correspond to the X dimension and the Y dimension. Another way of putting this is that the data varies or has variance in 2 main directions. It has variance in 2 main directions as shown by these red lines. Yet another way of saying it is instead of saying main directions, we can say it stretches in 2 principal directions. Principal means important or main, okay? So, and that's where kind of the word maybe principal components comes from, okay? We'll talk about why it's called component a little bit later. Actually, I can tell you right now, since these 2 directions are at 90 degrees to each other, these 2 directions are unrelated to each other. 90 degrees means orthogonal, not related to each other. Component means the means 2 ways in which something is different in an unrelated manner. Okay, so maybe, for example, for students, if I had to describe students, your academic ability and where you come from, like which city or state or country you come from, these are like 2 components of who you are as a student. They're not necessarily related, and oftentimes they're not related, where you come from and your ability. All right. So component means it means like dimensions or aspects of yourself that are unrelated. They are independent explanations of who you are. So principal components is really saying this data has a shape in 2 primary principal directions which are orthogonal to each other. But note that those 2 directions have nothing to do with X and Y. They're related to X and Y in some way, but they don't match exactly with X or with Y. All right. So that's the first introduction to principal components, all right? And what we can do with these principal components, how do they help us? Since these principal components of this shape are really describing the directions in which this data varies, and variance and varies is kind of like the directions in which it has meaning. What we can do is we can take another look at this data. We can forget the x-axis and the y-axis. We can take these 2 principal components or these 2 principal directions, and we can redraw our data based on these 2 principal components or these 2 principal directions, okay? So these 2 red lines that you saw up here, they're now the new axis of my data. I've just abandoned x and y, and I'm going to use those red lines to describe this data. You notice the data had an egg shape before? Egg, like dan egg, right? Shape before. And it again it still has this egg shape here because all I've done is I've taken this data and I'm showing it to you in a different way. I'm just kind of rotating it around in a way so that you kind of see that the first principal component, what we call PC1, is the direction along which the data varies the most. And the second principal component is after you have considered the first principal component, is the other direction at 90 degrees, unrelated to PC1, in which the data stretches, varies. Okay? So principal components allows us to take data that's described, in our case, measured by X and Y, and allows us to transform it into new measurements called PC1, PC2, where we're just redrawing the data on new axis. Okay. I'm going to get in a moment to why this is interesting and helpful, but just to kind of clarify once again, the first principal component, as you can see up here, captures the direction in which the data varies the most. All right. And the second principal component, that's the PC2, measures the way in which the data stretches the second most. right? And let me move on a little bit, and then I'll try to explain like how we use these principal components, okay? So let's look at what we just saw, but with the actual data, not with some imaginary XY egg shape, but with our actual data. And I'm not going to show you yet how I find these lines called PC1 and PC2. How am I computing them? We'll talk about that some other time, okay? But assuming we can do it, then let's take a look at it with our actual data. These, what you're seeing on this plot, are the actual 33 athletes. And they're measured, the x-axis is shot put, and the y-axis is 110-meter hurdles, okay? To be clear, if you're good at 110-meter hurdles, you should be low on this rating. You should be like further down here, like these few people here, these are like the best people at 110-meter hurdles, okay? For shot put, the best people are on the right-hand side because the better you are at shot put, the greater the distance we're measuring. So these people here are like the best at, maybe let's say these 3 or 4 are like the best at shot put, okay? Now, when we draw our principal components, we are finding the lines, or actually we can think of them as vectors, the lines along which this data stretches the most, all right? So PC1 seems to look like this, all right? It's quite parallel to shot put. And PC2 is this dashed line here. And it's not, I mean, and it's more parallel to 110 meters. But neither of these are actually exactly parallel to it, okay? Let's take a question. So Halim is asking, what's the difference between PCA and factor analysis for dimension reduction? Halim, you're way ahead of where I am. So let me get back to your question a little later, okay? Maybe not today, but maybe in fact next week, all right? So please bear with me. Shakane, or is it Kaylin? I'm not sure, is asking, if we have n variables, would we have almost n principal component vectors? Great observation. If you look at this picture, I have 2 principal components because I'm using a stupidly simple example with just 2 sports, right? I can only find 2 principal components because the data can only stretch in 2 dimensions. So you're absolutely correct. I only have 2 principal components here because I only have 2 dimensions of data. When I move to my 10-dimensional data set with 10 sports, I'm going to have 10 principal components. But then I can't visualize 10 principal components. I cannot visualize 10 dimensions. So I'm starting with 2, which is really simplistic and stupid, but let's go with it for a moment. So thank you for that question. All right. All right. And what can we do with this? So let's try to first find some useful things that we can do with principal components. All right. One thing that we can do with it is called dimension transformation. And what that means is you see how my data, it really matches the directions of PC1 and PC2, right? Like it's really goes along the line of PC1, and the width of it, how wide this data is, goes along, PC2. The original dimensions, neither of them exactly matches the shape of the data. So one thing we can do with principal components is we can transform the data so that, let's take a look at this. In this picture on the top right-hand side, I'm redrawing this exact same scatter plot. The scatter plot is exactly right here, the same 33 points, but this time I'm drawing them along PC1 and PC2, all right? Now, one more thing, notice that shot put and the x-axis and the y-axis, my original x and y, have a direction. Shot put increases as I go to the right. 110 meters, the time it takes to run increases as I go up, all right? PC1 and PC2 also have directions. You can see which direction it's going in when let's just take one point, like this point right here. This point right there has a value of the shot put value is 16.07. The 110-meter hurdles is a remarkably similar number, 16.06. This is in distance. This is in seconds, I take it. All right. Now, when I transform them using PC1 and PC2, what it does is we suddenly forget the original dimensions, shot put and 110-meter hurdles, and we look at it in this dimensions of PC1 and PC2. And in these two directions, 0, 0 is somewhere near the middle of my data, okay? And every point now has a value that's on a new PC1 axis, PC2 axis. So for example, this point we saw earlier with shot put and 110-meter values of about 16 point something, there it's now right here. And its new value is minus 1.94 in PC1 and minus 1.27 in PC2. All right. So one thing we can do, and the value of it may not be clear right away, is that we can take data that's on a measurement axis that how we measured it, and we can transform it to a new set of axes. The special thing about these new set of axes is that these new axes really run along the directions, the major directions of this data. Okay. So these dimensions describe the data closer to how the data would describe itself. Not necessarily for human beings would describe it, it's the way the data would describe itself. All right. So that's one thing to note. Using principal components, we can transform the data, we can rescale the data and rotate it in a way that its new axis is really aligned with the ways in which this data really varies. Okay. The original data was measured for convenience for humans. We can measure shot put with a ruler or with a long tape. We can measure 110-meter hurdles with a stopwatch. So we measured it in those ways because that's the ways humans can measure it. The data doesn't stretch in those directions. The data stretches in the directions described by PC1 and PC2. Okay. Why this is useful, we'll talk about another time, but notice we can do this thing called dimension transformation with it. Okay. We can take two-dimensional space, rotate it into another two-dimensional space, which is more aligned with the data. That's the first thing we can do with principal components. The value of it, again, please hold on. We'll see the value of it in the coming week or two. The second thing we can do is called dimension reduction. With dimension reduction, what we can say is we can say, instead of looking at all these values as being in two dimensions, like for example here, this point, which was earlier right there, this point right here, it's in two dimensions, right? PC1, PC2, it's got scores in both PC1 and PC2 dimensions. We can reduce the dimensions. We can get rid of one of the dimensions and reduce it, for example, from two-dimensional space to a one-dimensional space where all the points fall on a single line. Which line? Well, we typically, if we were to reduce it to one dimension, we would typically pick PC1. Why? Because that's the direction along which the data varies the most. It has its most variance along this direction. Okay. And we can now reduce, for example, what was earlier this point with PC1 and PC2 scores, we can reduce it to this point along just the PC1 axis, and we can just say it's got a PC1 score of minus 1.94, so its one-dimensional score is minus 1.94. All right? So this is called dimension reduction. Now, clearly, we could have done that with our original data as well, right? We could have taken shot put and 110 meters, and we could have dropped one of them and said, we're only going to use shot put. But think about this. Shot put and 110 meters, if you just take one of them, you're losing all the information about the other sports, right? If we just reduce the dimension by dropping one of these sports, let's say we dropped 110 meters, we only took shot put, then we're losing all the information about 110-meter hurdles. But when we do dimension reduction in PCA, you notice that these two principal components, they're not the same as shot put at 110 meters. PC1, this vector called PC1, as it increases, the shot put value changes and the 110-meter value changes, right? It's got a slope. PC1 has a slope in the shot put direction and the 110-meter directions, which means PC1 is capturing some information from shot put. It's capturing some information from 110 meters. So when we reduce the dimensions to just one principal component, PC1, we have some information about shot put in PC1, and we have some information about about 110 meters also in PC1. So using PC1, I can somehow capture a little bit of information about both the original dimensions in a single dimension. All right. So I'll take some questions here. Yenu asks, so if the shape varies mostly on PC2, will we pick PC2 to be this dimension reduction? That's a trick question, Yenu, and I know the trick you're trying to play on me, because by definition, PC1 is the direction on which it has the maximum stretch. If the other direction had maximum stretch, then that other direction would be called PC1. Okay, so Yenu, by definition, PC1 is the direction of the maximum stretch. You almost fooled me. All right, great. Does that answer your question, Yenu? I hope so. All right, great. Let's look at Gil's question. Does it depend on the axis which has greater variance of data? Yes, Guild. Guild, that was Guild. Oh, Gil, that answers your question. No, I haven't answered your question, Gil. I'll tell you why. Your question is a little bit more complicated, and I'll tell you why. You're asking, does all the story I just told you depend on the axis which has greater variance of data? The answer is yes, it does. And I'm going to come back to it because there's an issue there that makes what I just showed you a little problematic. Okay, let me go to Hannah's question first. How do we know which principal component is where the data varied the most? Okay, how do we know which principal component is where the data varied the most? Well, the technique that I'm going to show you, called principal components, will compute for you the direction in which it varies the most, and it will call that direction PC1. Okay, so the technique, I'll show you the technique today. I'll just show you how to execute it. Maybe next week I'll show you how it works a little bit more. But this direction automatically tells, PC1 automatically tells you, and there's a calculation it performs to figure out which direction. Roughly speaking, it's looking at variances in two directions, and it's asking in which direction can I find PC1 such that it goes along the maximum stretch of this data. Okay, and okay, all right. Okay, and as you can see, the direction of PC1 is the direction in which the data stretches the most. All right. I'll get to how this is kind of maybe computed and things maybe next week or some other time. All right. But for this week, I want us to get familiar with the tool and try to use the tool to solve some problems. Then next week, we'll come back and ask what if, how does it, all these questions. All right. Okay. Now, why we like principal components is it's very data driven. It tells us what the data thinks, not what the expert thinks. So in this picture, it looks like, PC1 is more important, and the reason it's more important, and let me describe the reason why it's most important. But there's two reasons. The first reason is an unfortunate reason, and I'll try to solve it in a second. The first reason might be, it's possible that the way I measured shot put, maybe the numbers of this measurement are the reason why there's so much variance, right? For example, let's say I'm measuring shot put in meters, okay? Now, you'll notice, by the way, another reason I picked these two sports is because they have roughly the same scale. One varies from about 11 to 16, the other varies from about 13 to 18. I mean, they have roughly the same scale, okay, but different units. But what if I measured shot put not in meters, but in centimeters? Then these numbers would be like 110 to 160. The variances would be huge because the scale, the numbers are so big. All right. So one unfortunate thing about principal components is that if one of your original scales has bigger numbers, like centimeters instead of meters, and it has numbers in like the hundreds, then of course it will have bigger variance because you're measuring it on a scale with bigger numbers. So that's, you can kind of get the wrong impression by doing principal components on data like this. Okay. So usually what we do is, since PCA is heavily influenced by the numbers on the scales, a safer thing to do is to standardize the data before you do PCA. If you standardize the data, then all the data is on roughly the same scale, no units, and the scales are roughly -3 to 3, right? Then you can get a much more fair idea of which direction has more variance. All right. So let's take a look at it. I'm going to scale my two problem. DEC2 is the two-dimensional decathlon problem. I'm calling it a biathlon problem. All right. And if I scale it and then ran PCA on it, the picture will look a little bit different, but essentially it's the same points on a different scale. All right. So the shape of the data should not have changed. The shape should be still the same. Remember, when you scale data, the distribution doesn't change, the scale changes, right? So here, the shape of the data shouldn't have changed too much. It's just the scales that have changed now. And the scales are now much more comparable. They're in both directions. They're from roughly -2 to 2 or -3 to 3, okay? Um, so, and yes, indeed, now some of the values will be negative. In fact, half the values will have a negative shot put score and half will have positive. Half will have a negative 110 meter score, half will have positive. So Mehtab, you're asking a question about after we do the standardization, some values will be negative. That's because standardization does mean centering and then divide by the standard deviation. When you mean center data, half the data becomes negative. Okay, Mehtab, does it answer your question? Oh, yeah. Okay, yeah. Here things are becoming negative because here, Mehtab, since the new axes, PC1 and PC2, are trying to describe the data, what better origin to have than the center of the data? So it's going to consider the center of the data to be the origin of the data, which makes a lot of sense, right? Earlier with raw units, your data can be way far away from the origin, which is maybe the human perspective based on how you measured it, but the data is like, why am I so far from the origin, right? So if the data had to pick an origin, it would pick its own middle. So that's the middle of your PC scores as well, all right? So similar, okay, and then when we standardize it, it looks like this, all right? Um, And all the things I described before, dimension transformation, dimension reduction, you should probably prefer to do it on this standardized data. So let's take a look at what we have here now. Let me see what the next slide is about, then I'll come back to this. Okay. Oh, okay. So I have now standardized the data. So shot put and 110 meters, these are now standardized shot put and standardized 110 meters. And this is PC1 and PC2. Okay. When I rotate this data and show it to you from the perspective of principal components, not the original messy units, those human units, forget the human units, think like a machine now. From the robot units, our data is now looks like this along PC1 and PC2. And the data loves this. The data loves this because the origin is at the middle of the data cloud. And the axes are, the first axis, PC1, is along the direction of the largest stretch, maybe because there's an outlier out here. And the second direction is in the direction of the second largest stretch. okay? Now let me try to unveil why we like principal components. So remember we were asking, how do we weight this data? Like, should we give more weighting to shot put? Should we give more weighting to 110 meters? Wouldn't it be unfair if we did it one way or the other way? Principal components allows us to create a composite with weighting that is data driven. And let me back up a little bit and show you how. If I wanted to create, where was it? This composite score, a single score of, okay, for decathlon, but in this case, the biathlon, the two sports. If I wanted to combine these two into one score, one number, one variable, then one way to do it is the following. We can do dimension reduction. We can throw away the second principal component and keep the most important principal component, PC1. Okay? And remember, PC1, it's not just shot put and it's not just 110 meters. It's got a little bit of both. It's got a little bit of shot put and a little bit of 110-meter hurdles in it. Okay? Now, which one does PC1 weight more? Shot put or 110 meters? Looking at this picture, okay, I mean, we look at the standardized picture in a moment, but if you were to look at the raw units, then it would appear that shot put, that PC1 seems to be more related to shot put on the raw units. Okay, it's favoring shot put a little bit more. When we standardize it, it's a little bit difficult to tell. It looks like it's kind of weighting both equally. All right. Now I have to tell you a very unfortunate part of the story. We almost never do principal components on just two variables, because when you do it on two variables, like I'm doing for this visualization reason, it will weight both equally. All right. It's just an unfortunate characteristic of PCA. If you do it on more than two dimensions, 3, 4, 5, 6, etc., it will weight them unequally. All right. And the way it will weight it is PC1 will capture, your original dimensions. It'll capture all of your original dimensions in slightly different ratios. All right. In the standardized example, it looks like a 45-degree line. So it seems to be capturing shot put and 110 meters equally well. Like it's giving almost equal weighting to both. PC2 is also giving equal weighting to shot put and 110 meters. Okay. But if we look at, when we go back to the 10 variable example, we'll see it's not equal weighting for more than two variables, but bear with me for a moment, okay? All right, now, if we were to do dimension reduction and get rid of PC2 and only keep PC1, why is PC1 so important? It's important for the following reason. PC1 will capture the variance in the greatest direction of variance. Why is that important? It's important because consider that all these athletes have trained as hard as they can, okay? They've trained as hard as they can. And if everything was equal, then this data cloud should be a big circle, but it's not. You can see here that some people are scoring more differently in this PC1 direction. Like some people are scoring really back here, some people are scoring all the way up here. Okay. And essentially what's happening here, and by the way, if you kind of follow these rotations, and I'm sorry, we're rotating the data so many times, but if you follow the rotations, I believe this person right here, oops, excuse me, this person right here, of these three people, this person right there in the middle of this circle, that's the person with the smallest PC1 score, but that's the person who corresponds to the best combination of shot put and 110-meter hurdles. Okay, that's the person who corresponds to the best combination of shot put and 110-meter hurdles along the direction of maximum stretch. Yenyu has a question, and let me look at her question really quickly. Will there be circumstances that PC1 nearly equals PC2? Yes, there will, and that's this example where I have only two dimensions, Yan Yu. Okay, when we look at more dimensional data, they will all vary quite a bit differently from each other. All right. So what I could do with principal components, very briefly, is I could reduce it to one dimension, PC1, and I could declare this person right here the winner. Why? Because this person, as measured by PC1, and PC1 captures shot put and 110-meter hurdles, weighted according to the data, and performs the best in that direction. And usually PC1 is the direction in which there's a maximum variance. And that's important because that's the way we can discriminate the best between all the different participants. All right. In the other directions, there is less difference between them. So we can say the best way to distinguish these people and to separate them out the most is along PC1. Okay. And so PC1 gives me a way to pick a winner and say this is the number one athlete according to 110 meters and shot put. All right. Okay. Um, and so that's one way in which principal components is used is for dimension reduction. We can just abandon all the dimensions except for PC1 and say this is the direction in which the data stretches the most. It seems to be where the most differences are between the people, and let's score them on the direction of the maximum differences. All right. So that could be one use of principal components. So this would be the gold medal. This person might be the second place or silver medal. And I think this person right here, would be our third place winner and get a bronze medal. All right. So this is one way we could use principal components. And notice principal component one, like all the principal components, captures something from each direction. All right. Let me go through the rest of this a little bit quicker. So I've given you the basic idea of principal components. Let's dig into some numbers. We can actually get some numbers out of principal components in the following way. We can, and let me do this with a two-dimensional example. We can use this function, which comes with R. You don't need any special package for it. So we can take the correlation matrix. Remember, we had this correlation matrix before, but this time it's just for the two-dimensional data. Okay, we can take the correlation matrix, the two-dimensional data in this case, and we can run this function on it called eigen. And let me show you what eigen gives you. Okay, eigen gives you two things. It gives you values and vectors. Okay, first of all, eigen is I think it's a German word originally. It's a German suffix originally, and it kind of means belongs to itself or its own thing. You can kind of think of it as meaning unique. All right. So these are some unique ways of describing this data. It gives you what's called eigenvalues and eigenvectors. Let's talk about what these are really briefly. Okay. The eigenvectors, if you look at them like this way, are telling you, and this is the matrix that it gives you for eigenvectors. It's giving you two column vectors. So here's the first column. Here's the second column. What are these columns telling you? The first column is the vector that we use to draw PC1. This is the direction of PC1. All right. So these two eigenvectors are the directions of PC1 and PC2. In this really simplistic example of two variables, you'll notice the numbers are like 707 in every quadrant is because it can't really discriminate between just two variables. More than two, and you will get different values, okay? But for now, just take a look at this. It's telling us in the standardized example that PC1, the direction of PC1, that line or that vector PC1, is 1 unit of change in the PC1 direction. So let's say we stepped 1 unit in PC1's direction. That 1 unit corresponds to a minus 7.07 drop in shot put and a 0.707 increase in 110 meters. So let's do that. It's going to be, so that would mean I have to go down in shot put and up in 110 meters. So that tells me that the direction of this vector is like this. It's almost a 45-degree angle, well, more or less. And it's kind of like in this direction, all right? And for PC2, the direction of PC2 is identified by the second column. And it's going negative, is going down in shot put and down in 110 meters. So PC2 is actually going this way. This is the direction of PC2, all right? So these eigenvectors tells me the direction of these two principal components. So that's the first thing to understand about principal components. So let's look at some questions. Oops. Oh, okay, no, we have no new questions, okay? So the eigenvectors tells us the direction of these two principal components. That's fantastic. The directions relative to the original dimensions. So the first dimension of this column vector will be shot put. The second dimension will be 110 meter hurdles, all right? Notice when it gives you the direction, that these two column vectors, if you look at their length, their magnitude, you can compute the magnitude like this. We saw this a few weeks ago. To compute the magnitude of a vector, you just take the square in both directions and you add them up and take the square root. You will see the length of these vectors is 1. The eigenvectors always have length of 1. It's not telling you which one is more important. It's just telling you the two directions. So the eigenvectors by themselves don't tell you which is more important. They give you a hint because the first eigenvector is PC1, so you know which is more important. But the actual numbers in here don't tell you because they both have unit length 1, okay? If you want to really know which is more important, of course, you know that this one will be PC1. But if you want to know how much more important, then you look at the eigenvalues. So if I was to kind of just run this eigenfunction and store it in a variable called EG, then EG dollar vector, vectors tells me gives me a 1 unit vector in the two directions. But which one is more important? The eigenvalues will tell me. The eigenvalues will tell that to me, okay? The eigenvalues in this case is 1.29 and 0.7. It's not symmetric. And what it's telling me is that the first principal component, all right, captures this much variance in the data, and the second principal component captures this much variance in the data. The variance of what? Well, the way you can think about it is like this. If I took these two eigenvalues, okay, and I added it up together, guess what I'm going to get? I'm going to get the number 2. Why the number 2? Because my data was originally in 2 dimensions. So what these eigenvalues are telling you is of those 2 dimensions, how much of those 2 dimensions does PC1 capture? It's saying PC1 is capturing roughly 1.3 out of those 2 dimensions. Okay, so it's capturing, if the information we had was in 2 dimensions, PC1 is capturing about 1 1/3 dimensions of the information. PC2 is actually capturing about 2/3 of a dimension of information, given that we started with 2 dimensions. All right. So the eigenvalues will always add up to the number of original dimensions, because what they're telling you is of the original dimensions, how much of those original dimensions is captured by each principal component. And here again is why we like PC1 so much. It's capturing not just 1 dimension worth of data, it's capturing more than 1 dimension worth of data, which tells us it's capturing some information from multiple dimensions, which is great. Okay? I'm not going to try to over-explain it today. So the eigenvector tells you the direction of variance, eigenvalue tells you the magnitude of the variance. Okay? Let's see quickly. I've got 5 minutes, but I'm going to go a little bit over time. I'm so sorry about that, folks. How many slides do I have left? Let's take a look. I have 1, 2, 3 slides left. Okay. Um, so another way of getting these eigenvectors and eigenvalues is another function. It's called PRComp, and it also comes with R. Okay, it tells you almost the same information, but it's got a couple more things in there that are interesting that we can play with next time. Let's take a look at PRComp. Where is it? Where are you? Here we are. So let's take the two-dimensional um, biathlon data example, and I can run PR comp on it. I'm saying scale equals true. I'm telling it, please standardize the data. Generally speaking, always standardize the data. There's some unusual cases where we don't standardize the data, but when we're trying to interpret principal components, we definitely standardize the data. Okay. So here we standardize the data, and this runs principal components analysis for us. Um, we can take the object that's returned to us. It's got a bunch of interesting things. One is you can just plot it directly, and it shows you a really interesting plot. This is showing you the plot of the 33 athletes, each of them numbered, right? So that's really cool. Instead of showing you dots, it's showing you like this was the row number 1, this was row number 33. Okay. And it's showing it to you on the directions of PC1 and PC2. The origin is somewhere here in the middle. The origin is right about there. Okay, the origin is right there, and it's showing you the data as it's separated on PC1 and PC2. What's also really interesting is it shows you the original dimensions of shot put in 110 meters from the perspective of the principal components. So as you can see here, as we go up in principal component 1, as we increase in PC1, we are effectively going down in shot put and up in 110-meter hurdles. That's exactly what the eigenvectors told us. You're going down in shot put and up in 110-meter hurdles. Okay? And if you go up in PC2, then if you're going up in PC2, you're basically increasing in both dimensions. All right? What else does PRComp give us that eigen does not give you? So let's look at DEC2 PCA dollar. I'm not going to look through all of them. The only other thing I'm going to show you that the eigen function does not give you is PRComp actually gives you the scores of the original 33 athletes, but this time it gives you the scores in the units of PC1 and PC2. All right, so that's really cool. It gives you scores in the units of PC1 and PC2. Okay, so with eigen function and the PRComp function, you can get a lot of early, easy stuff to play with that gives you a lot of important information. I'm going to go a little bit over time. I'm really apologize, but let me try to cover the rest as fast as I can. Okay. I want to do everything we just did, except I want to go back to the 10-dimensional data. Okay. Let's go back to the 10-dimensional data. All right, I'm going to wipe this out. And I cannot visualize the 10-dimensional data, so I'm not going to bother with the visualizations. Let's go with the 10-dimensional data. And in this case, what I'm going to do, okay, is a few things. One is I can run my eigenfunction on it. All right. I can run my eigenfunction on it, and this gives me eigenvectors and eigenvalues. Alternatively, I can run the PRComp function on it as well. This is just another way to do the analysis, okay? And when I take a look at it, it will also give me like eigenvectors and eigenvalues, but with a little bit of difference. And let me explain what the differences are here, okay? So let me see how to kind of look at this, okay? So one thing I want you to notice is that it's a little arbitrary. So I think someone asked me earlier that, hey, when I did the principal components on it, some values are negative, right? Well, which direction does PC1 go? Is it like always the same direction? Unfortunately, depending on which statistical function you're using, which algorithm you're using, the direction of the vectors can be flipped. So the eigenfunction and the PRComp function, they'll give you the same principal components, but sometimes they're pointing in opposite directions. So you just have to be aware of the directions in which it's pointing, okay? So let me look at it from what's on the handout here, okay? So we don't get confused. So, excuse me. Oops. Okay. All right. So I'm going to run PR comp on the entire data set scaled. This gives me eigenvectors. All right. And you notice my eigenvectors, they're the negative, they're the opposite of what eigen gives me, but it's the same vectors. This time, PC1 is a vector along 10 dimensions, which is my 10 original sports. Okay? So PC1 is capturing some amount of all 10 different sports. PC2 is capturing an orthogonal principal component, an orthogonal component, which is 90 degrees to PC1. So it's the second most important direction of these 10-dimensional sports. PC3 is capturing a third orthogonal direction all the way down to PC10. PC1 through PC10 are 10 vectors which are all 90 degrees to one another. I can show you like vector 1 and vector 2, 90 degrees. I can show you vector 3 would be like 90 degrees to the first two. I can't show you vector 4, 5, 6, 7, 8, and 10. Okay. What's really cool though is you're also getting a sense of what each principal component means. Because as you can see, PC1 seems to be, what are the biggest values on PC1? It seems to be most heavily correlated with the direction of 110 meters, long jump, 400 meters, 110 meters, and pole vaults. Interestingly, those are all the sports that require running really fast. Okay, so that's kind of interesting. PC1 is capturing a lot of variances that are coming out of the running sports, with the exception of high jump, very low on that because apparently you don't need to run very fast to do the high jump, and 110 meters. You need to run, but not very fast. Okay. What is PC2 mostly related to? Its biggest correlations are with shot put, 400 meters, discus throw, and potentially javelin and 1500 meters. If I looked at some of these, like, shot put and discus throw, it seems like you need to have like really good strength. Maybe lower body, maybe upper body, I don't know. You also need that to throw a javelin. But interestingly, it also captures a lot of what we call endurance, like 1500 meters. So it's capturing something between power and endurance. Okay, and this is the cool but weird thing about principal components. They're not Principal components are so data driven, it won't match a single human dimension perfectly. But it will say the data is telling us that the second direction of stretch is something that captures multiple things. 110 meters, capturing either sprinting ability, maybe, or maybe it's capturing, this is also pole vault, you need to sprint like crazy. The second dimension, the second principal component seems to be capturing like raw lower body strength, I guess, lower body and upper body strength. Okay. Is there a third dimension? Yes. Wow, look at the third principal component. It's huge. It's got a very strong correlation with high jump. High jump appears to be a very unique sport, apparently, because not PC1 and PC2 were not as correlated as PC3. PC3 is saying high jump is a dimension of its own. All right. So we can start looking at these eigenvectors and treating each of these as something like a correlation. It's telling us how much it would change, in the standardized direction of high jump if we moved one standardized direction in PC1. So that's essentially telling me a correlation. If you look at the summary of this principal component object, PCA object that I get from PRComp, it gives you some more things that are interesting. It gives you this proportion of variance. It tells you, these are our eigenvalues from before. Okay, these are our eigenvalues. And what it's done in the second row is it's basically divided each of these. It's divided the eigen. Oh wait, are these the eigenvalues? Excuse me. No. Let me quickly look at eigen core deck. No, these are not the eigenvalues were like 3.41, 2.60. What the summary of deck PCA is doing is it's taking the eigenvalues and has divided them all by the number of dimensions in my original data. If I had 10 dimensions, divided by them all by 10. So remember, the eigenvalues tell you how many of the original dimensions is captured by each principal component. So the first eigenvalue of 3.4 is saying the principal component 1 is capturing 3.4 dimensions worth of information. And this proportion of variance is basically that eigenvalue divided by 10, because we have 10 dimensions of original data, is telling us that about 34% of the original data is captured by the single principal component. Think about that for a second. We had 10 dimensions. 34% of it, a third of that information, is captured by a single principal component. That's amazing. That's a lot. Okay. The second principal component captures about 26%, or about a quarter of the information of the variance of the original data. The third principal component captures about 9%. The bottom line is telling us cumulative, so it's telling us the first principal component captures 34%. The first two principal components captures 60%. The first three principal components together captures about 69 or 70%. All right. So this is what principal components does for us. It takes data and it kind of tries to find what are some dimensions to the data which can capture the variance more efficiently than the dimensions you're using to measure it. Okay, so it's an extremely efficient way of capturing information with the fewest number of dimensions. Of course, because we have 10-dimensional data, it'll give us 10 dimensions of 10 principal components. But as you can see, by the time we hit 6 or 7 principal components, we've captured like 9/10 of 90% of the original information. All right. I'll do one last thing before I let you go. And I'm so sorry to run over. I'll do one last thing. It must be bothering you that, well, we have now 10 principal components. Well, I originally had 10 dimensions of data. How many principal components is useful, and how many can I get rid of? All right. There's two ways to answer the question of how many principal components captures enough of the variance of my data that I can look at a reduced set of dimensions, right? Because, for example, someone might say, hey, I can reduce all the athletes to just PC1. That's great, because deck PCA, if I reduce everyone to one principal component, which is just PC1, that's this vector right here, that gives me a single score for the 33 athletes. Why is that good? Because then I can use something like that. Oh, excuse me. Whoa, what happened? Excuse me. So what that's good for is I can use PC1 to rank order the 33 athletes. Oh, sorry. I can use PC1 to rank order the 33 athletes. So either this one or this one is going to be the winner, depending on which direction PC1 is heading. Is it heading in the direction of the best performance or the lowest performance? So depending on the direction, that would be the best performing or the worst performing. Okay, and so that's why I might want to reduce it to just one dimension. But there are times, and I'll show you an example in the coming weeks, where we want to reduce the dimensions, but not to one dimension, but to as few dimensions as possible to capture as many important dimensions as possible. Like if we want to understand what are the important dimensions of this data according to the data itself, how many dimensions, how many piece principal components do we need to look at? Because remember, I was interpreting PC1, I was interpreting PC2 by looking at how it correlates to things. Do I need to continue that comparison all the way down to PC10? That would be crazy. It would be nice if I could define athletic ability, that construct, that component that I was looking at earlier, with as few dimensions as possible. So how many dimensions do we need to kind of come up with a definition of athletic ability? There's two ways to do it. So remember, I interpreted PC1 as sprinting performance. Okay. I interpreted PC2 as like some kind of strength, discus, right? I interpreted PC3 as high jump, and it's not really correlated very well with anything else. PC4, it's correlated with javelin. Well, every principal component is going to be correlated with some things. How many should I interpret is a question. Okay, how many do I need to interpret to capture the important dimensions? There are two ways to decide how many principal components to use. Let me describe these two ways, these two criteria. There are some people who say, just look at the principal components who have eigenvalue greater than 1. Okay? Why? Because remember, the eigenvalues tells you of the original dimensions, how much information of those original dimensions does each principal component capture. So the logic is PC1 captures like 3.5 dimensions worth of information, so it must be quite important. PC2 captures 2.5 dimensions worth of information, so it must be important. But all the other principal components, they are less valuable than 1 dimension of my original data. So let's forget about them. Okay? So some people use this criteria called eigenvalue greater than 1. They say, if you're just interested in interpreting what are the important dimensions, just look at principal components with eigenvalue greater than 1. So in our example, we would interpret only PC1 and PC2 and say that athletic ability is a combination of, what is it? Running power, running speed, and some kind of physical strength and endurance. So somehow those things put together could be athletic ability. And you can ignore the other dimensions. Okay? That's one way of saying I don't need to interpret 10 dimensions, I only need to interpret 2 dimensions. And this eigenvalue greater than 1 criteria tells us we only need 2 dimensions. Now, there is another method which I kind of like. It's a very visual and interesting method. The other method is called a scree plot. Um, and let me show you what it is and then tell you why it's called a scree plot. The scree plot basically does this. The scree plot looks at the eigenvalues. By the way, you can get a scree plot by just calling the scree plot function and giving it your PCA analysis from PRComp and saying type equals lines. It will draw something like this. So I think if I do scree plot, it comes with R, the built-in stats package. Deck PCA type equals lines or L, whatever. Okay, it'll draw a picture like this for me. And the way you're told to interpret a scree plot is this. The y-axis is how much variance does each principal component capture. The principal components are on the x-axis, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because we have 10 dimensions of data, so we have 10 principal components. The eigenvalues are on the y-axis. And remember, the eigenvalues tell you roughly how much variance does this capture given the original number of dimensions. So the first principal component was like 3.6. The second was the first one was a 3.4. The second was 2.6. All right. So the scree plot basically says, look, this has a lot of variance. This captures also a lot of variance. But from the third principal component to the 10th principal component, there's a very linear, like they just capture a little bit more variance than the last one. So PC10 captures very little variance. PC9 captures a little bit more than it. PC8 captures a little bit more. Now, these are like all incremental value. They don't have that much value. The ones you should be interested in are the ones after the elbow, like if you have an arm and you have an elbow right here. So after the elbow, when it jumps up high, these are the ones you're interested in, PC1 and PC2. So it's the scree plot is a visual way of picking the number of principal components that are important. And it just says capture the ones which have very high variance explained, so much so that all the others seem to follow a simple line. Okay. So these are two ways in which you can kind of ask, you can decide how many principal components do I need to interpret to understand the important dimensions of my data. By the way, why is it called a scree plot? It's a very English word, the word scree. If you have a mountain, like this is a mountain, right? In this picture, in this photograph, at the bottom of the mountain, you will have a slope with all the rocks that have fallen off the mountain. This slope with all these rocks is called a scree. It's all the loose stones and they're unimportant things that fell off the mountain. All right. So this area here is called the scree. And the scree plot is telling us, just look at the mountain. Don't look at all the scree at the bottom. Okay. So this is all my slides. And let me just go back to what I originally was doing all this for. My original question was, how many unique dimensions of athletic ability are represented by these 10 sports? According to what we saw today, and I will challenge next week what we saw today, but according to what we saw today, there are two important dimensions to athletic ability. If I can assume that this data captures athletic ability, but we know it captures Greek, Roman, Western concept of athletic ability. So given that, there seems to be two dimensions. The most important dimension seems to be around running ability or running power, sprinting power, not just running a long distance, but running fast for a short distance. So explosive running power. That seems to be the first important dimension of athletic ability, the most important dimension. Why is it important? Because that's the dimension that is hardest to master. Some people get very low scores, some people get very high scores in that direction. In all the other directions, people's scores are much closer to each other. The second most important dimension seems to be some combination of strength, like shot put and discus, but it's also somehow correlated with 400 meters and 1500 meters. So it's a little bit hard to interpret, unfortunately. All right. But if we can create a dimension called strength and stamina, it's some combination of those two things is the second dimension. All right. And the data, not experts, the data is telling me those are the two important dimensions in that order. So that is what athletic ability is. Okay? All right. So that is a purely data-driven approach to interpreting what is the important dimensions to my data. All right. I want you to go home and, well, you are home. I want you to stay home, first of all. And I want you to do a homework assignment where we're going to ask you to use PCA on a data set and try to interpret it in some interesting ways, okay? Using what we saw in class today. Next week, we're going to come back and take a deeper dive, a deeper look into what PCA is, how it works, what it does. And we're going to challenge some of the assumptions we saw today. And we're going to challenge some of the advice I gave you today. All right. So I'll let you go with that. Thank you all for being so good and waiting for me for about 20 minutes after class time. Again, it's difficult to manage this thing online. And everything is recorded and on YouTube. So try to do the homework assignment, ask as many questions as you can on the discussion board. We'll get through it. And if you don't understand exactly what PCA is doing, don't worry as long as you're able to do the homework, because then you'll know how to drive this car called PCA. Next week, we'll dive deeper into what is it doing, what does it mean, what is it all about. Okay? All right. Thank you all so much. Have a great week and